Hello, this is Hossein Talebi. I'll be presenting our paper on rank-smooth pairwise learning in perceptual quality assessment. This is a collaboration with my co-authors Ehsan Peyman Milanfar, and Manfred Warmuth. Conducting pairwise comparisons is a widely used approach in perceptual study. Based on this framework, human readers are provided with pairs of images, and they are asked to make their selections based on some notion of image quality or image aesthetics. Once the perceptual study concludes, the image data, along with the reader's preference, is used in a learning framework to train a model. However, training on pairwise comparisons through mini-batch learning can be challenging. Assuming that we use gradient descent to optimize the underlying model, at each step of the gradient descent, the model only gets to see pairs of images, meaning that the global ranking of the images is not incorporated or fed to the model in the training process. In this work, we propose a novel approach by incorporating the global ranking into the pairwise training framework. More explicitly, we approximate the global ranking of the image objects, and we fed them to the learning process, and we show that this can effectively improve performance of the underlying model. Here we show an example of pairwise perceptual study. In this example, human readers are asked to select the image with better quality. Note that image A and image B could have similar content or completely different content. It's worth noting that comparisons are performed on a subset of all possible pairs. Therefore, we call them local comparisons, and we differentiate them from the global comparisons, which includes all possible pairs. For instance, for n images, the total number of comparisons in the global comparison set is n choose 2. Also note that the pairwise comparisons are repeated multiple times across different evaluators. This can help to reduce the label noise. Once the comparisons are concluded, one can obtain the empirical preference of image I over image J by dividing the number of times that image I was selected over image J across different evaluators by the total number of comparisons for that particular pair. Note that this is the maximum likelihood estimate of the Bernoulli random variable that picks image I over image J. RankNet is perhaps the most commonly used approach for learning to rank from pairwise comparisons. In the RankNet framework, the cross-entropy loss is used to train parameters of a CNN that predicts the preference probability of image I over image J. Note that in this cross-entropy loss, the empirical probabilities from pairwise comparisons are used as the ground truth. This diagram shows the RankNet framework. Note that the local empirical probabilities are used as labels in the cross-entropy loss, and image pixels are used as input to the CNN model. The CNN model is trained through weight sharing. The output of the CNN is the probability of preferring image I over image J. Our contribution in this work is to add an approximation of the global preferences of image pairs into the cross-entropy loss. The net effect of this change is that at training time, the CNN gets to see not just the local pairwise comparisons, but also an approximation of the global ranking. Such approximation is obtained through rank aggregation. Next, we discuss more details about our proposed method. If we take a closer look at our training loss, you can see that it has two terms. The local cross-entropy term, which is based on pairwise comparisons, and the global cross-entropy term, which is based on the approximated rank of all images. If we expand our training loss, we can see that the net effect of combining the two cross-entropy terms is that we are smoothing the local empiricals with approximated global empiricals. The parameter alpha controls the trade-off between the local and the global loss in our training loss. Next, we discuss the rank aggregation method for obtaining the global empirical probabilities. The rank aggregation method suggests that forming a Markov chain transition matrix pi and computing its stationary distribution can help to provide an approximation for the global ranking probabilities. Such transition matrix is formed as follows. The off-diagonal entries of the matrix pi are simply the normalized local empiricals. The normalization factor is the maximum out degree of node I or image I. The diagonal entries of the transition matrix are defined such that the matrix pi becomes row stochastic. Once matrix pi is computed, the stationary distribution of pi can provide us with an approximation for the global empiricals that we were looking for. In many applications such as word embedding, smoothing the estimated probabilities of the items can result in improved performance. In this framework, we apply such smoothing on the approximated global empiricals. Note that the net effect of such smoothing with the parameter beta is that the distribution of the global empiricals can change from uniform to identity, or even we can create skewed distributions toward more popular items. Here we present our results on synthetic data. The synthetic data is randomly sampled from a power law distribution. As an error metric, we compute the KL divergence between the predicted and the ground truth probabilities. In this set of experiments, we explore the impact of the number of comparisons per pair, known as NT, on the optimal alpha, which is our blending factor, and beta, which is our smoothing factor. The plot on the left side shows that as the number of comparisons per pair increases, so does the optimal alpha. This means that the local comparisons become more accurate as we increase the number of comparisons. Also, the plot on the right side shows that as we increase the number of comparisons, the optimal beta gets closer and closer to 1, meaning that there is less need for smoothing. In this set of experiments, we explored the impact of the number of pairs on the optimal blending factor alpha and the optimal smoothing parameter beta. We denote the number of pairs by R as a fractional number that can take values from 0 to 1. As you can see in the plot on the left side, as R increases, the optimal value for alpha decreases and gets closer to 0. This means that as we increase the number of pairs, the local comparisons become less important than the global ranking. As we decrease R, you can see that the optimal value for beta also decreases. This makes sense because smoothing would help when there is more ambiguity in the data. Here we present our results on a large-scale perceptual comparison dataset. This dataset consists of 17 million pairwise comparisons from 250,000 unique images. Each image pair is rated by 5 human raters. We set a minimum of 13 pairs per image, meaning that each image is randomly paired with 13 other images. We trained multiple inception V2 CNN models, and we varied the parameters of our training loss, namely alpha, the blending parameter, and beta, the smoothing parameter. We measure the accuracy of predicting the perceptual preference of the human raters. As you can see from our experimentations, it seems that the optimal value for alpha is close to zero point 0.5, meaning that both local and global comparisons are equally important in the training process. Also, the optimal value for beta seems to be 0.95. This indicates that applying some modest smoothing on the global empiricals has helped. Here we provide some visual examples from the trained CNN. We present both the predicted and the ground truth scores from the live dataset. Images on the top row are either blurry or have bad exposure. On the other hand, images on the bottom row have better contrast, sharpness, and exposure. As you can see from the predicted score, the trained model can closely predict the perceptual quality of these images. In this talk, we propose a method for a more efficient learning from image pair comparisons. We showed that combining the pairwise empirical comparisons with the global ranking of image items can lead to a better training and more effective models. It's worth noting that our approach is also tested on generic synthesized data. This implies that our method perhaps can be employed beyond the scope of the image quality assessment. Thanks for your attention.